of Phobos. Let's see if I can do these slides. Yeah, and as Steve pointed out, I've been fortunate to lead a really talented and dedicated team across the agency to study the Phobos and Deimos human missions. I'm not going to tell you much about the science that you don't already know, so I'll skip that. But I will say that the Mars moons are interesting, certainly scientifically, and I've even gained to appreciate that more sitting through these presentations. They potentially offer engineering, operational, public engagement benefits that would enhance a subsequent Mars surface mission. The moons of Mars are possibly captured asteroids, likely contain Mars surface materials, likely contain materials from the asteroid belt. And they offer near zero latency teleoperations of Mars surface assets. So it's potentially an affordable and productive first step toward an eventual Mars surface operations. Also provides significant radiation protection. Both Phobos and Deimos are interesting destinations. With the current imagery, we know Phobos is a fascinating place. And it turns out that Phobos is the transportation driving case, so we spent most of our time working on the Phobos mission. When we started this out, as an astronaut, I wanted to get an intuitive feel of what this gravity level was like on Phobos, and this chart just shows that if I jumped off at a maximum jump in my suit, on our moon, you would go up about 1.2 meters. That's John Young jumping up, and it would take about 2.5 seconds. On Phobos, I would go up 350 meters, so about 1,000 feet, and it would be about a 12-minute round trip time, and Deimos is about twice of that. So as a crew member, I weigh about 1/3 of a pound. The space exploration vehicle I'll talk about later weighs about 8 pounds, and a large lander would weigh about 60, 70 pounds. So when we started this study, this is kind of the trade space. Destinations looked at Phobos only, Deimos only, and then a combination. For transportation, we basically were told to assume a conjunction class mission. We looked at direct to Phobos. That was not practical. It's very expensive to do the plane change. And so where we ended up is going Earth to Mars, inserting into a high Mars orbit, and then taxiing over to Phobos with a much smaller mass spacecraft. We also initially looked at some trajectories with hyperbolic rendezvous, and I was quite interested in that, but that sort of petered off. In terms of pre-staged assets, so the concept is we would either use a SEP or a chem-SEP hybrid, I'll talk about that more later, to pre-deploy some range of assets that range from nothing to a Mars-Moon habitat to a habitat plus pressurized excursion vehicles. As far as the habitat, we looked at surface habs, both static and mobile. And then we also looked at various parking orbits at the Lagrange points, L1, L4, and L5, and then DROs. In terms of what I call exploration work systems, we looked at jetpacks, unpressurized excursion vehicles, and then pressurized excursion vehicles with the SEV class. I'll talk about that more later, and also a Mars lander class. So I'll start with the radiation exposure. This is a bit of an eye chart, but these are the various launch dates. And then these are the different locations, and I won't bore you too much, but basically, the minute you get off the surface, even at L1, the radiation protection falls off dramatically. So, on any of these orbital assets, we're maybe reducing the total radiation dose by 3% or so compared to a high Mars orbit for the equivalent launch window. Whereas when you get on the surface, and we assumed a 10-degree crater rim, we ran the Alteris radiation dose model that was developed at Langley and also used at JSC. And we can save up to 34% of the total radiation dose on the crew, and that includes the outbound, the stay at Phobos, and then the inbound. So there's significant radiation protection. When we started this work, we actually built on work that Dan Mazurek had led, and we wanted to develop a reference science mission that we could use to compare different architectural options. I'm not going to bore you with all the details. This is a reference science mission. It's not necessarily the one that we would do, but a lot of thought went into it. We had a lot of help from Paul Abel, and Dan Britt was on our team, Pascal, Stan Love, and others. So it was a thoughtful development of a reference science program. So there were 11 regions Within each region, we had 5 subsites. And at each subsite, we had this area that Paul worked with us on that we called the area of 100-foot diameter area of geological interest. And within that area, we basically have a standard circuit where we get a float sample, a hammership sample, a soil sample, a core sample, and an instrument deploy. And these might not be exactly the task that you would do by the time we get to Phobos, but we worked very carefully with Dave Krang and others over the years to have this standard set of tasks that we use at Desert Rats and Nemo and all of our analog work. So the idea was to have this standard science mission. We developed 16 very detailed timelines, and we've actually done all these tasks either underwater in the desert and have very accurate timeline data for them. So we took all of those tasks and decomposed them into forces, torques, distances, accuracies, all these kinds of things. From that, we developed functional requirements of what our exploration system should be. And then from that, we brainstormed and had many, many different systems, but we down-selected to 3 basic ones. One was a jetpack, where we actually had another jetpack that was a mobile carrier that would carry your tools and samples. The other was an unpressurized excursion vehicle, kind of like a Segway thing that could hold your tools, have some additional power. It had hopper legs and an RCS sled, and then a class of pressurized excursion vehicles. The published escape velocity of Phobos is 11.4 meters per second, but when we got our smart guys with our GNC Copernicus guys to look at it, it turns out there's some low energy escape paths at the sub-Mars and anti-Mars point of 2.84 meters per second. So you could almost jump off the surface. We actually developed a high-fidelity physics sim of Phobos that we have this vehicle flying in. If you ever get to JSC, I'd be happy to show that to you. The other thing I would point out is that when we do these mission developments, we actually attack it like we're really the flight team and flight crew going to do the mission. So we write all these flight rules that would actually constrain us and so forth so that we have a high dose of reality. And one of the big drivers was we had a flight rule in Constellation that we had to be able to return to radiation protection within 20 minutes in case of an SPE. And so we looked at the Phobos gravity, and with jetpacks, we typically don't like to fly them faster than 0.5 meters per second. And that is actually set for damaging the suit. And so with that, if I can get this laser to work, to get back within 20 minutes, we couldn't go more than 500 meters from where the hab was. And then on top of that, so if we went faster, we could go farther. But I started looking at the orbital mechanics, and it is anything but intuitive. And the gravity is non-uniform and so forth. And you could picture a guy in a jetpack, trying to fly over here, and then he ends up higher, and very quickly finds himself on an escape trajectory running out of oxygen. So we basically ruled out jetpacks as not being safe and advisable. So in the PEV options, we looked at our evolution of the pressurized excursion vehicle with an RCS sled and hopper legs. We looked at it with a sled only. We looked at a habitable airlock-derived lander and then MAV-derived landers. We ended up selecting the SEV class rover, and this is an evolution from our lunar rover, where it basically has this RCS sled and hopper legs. We'd have an astronaut positioning arm on the front, and the crew would be working in a foot restraint off the arm. We actually did a high-fidelity sim of this, and I'll talk about that later. So this whole PEV is evolved from the lunar electric rover, and one of the key points of that that's relevant to the future discussion is that we have the suits on suit ports. The cabin is at 8.2 psi, 34% oxygen, which basically eliminates any long pre-breathe. And then the suits are hanging outside the vehicle. You open up a hatch on the inside, you open the backpack of the suit, you step into the suit, you close the hatches, you only have to depressurize the small vestibule between the hatches so you lose very little gases. You keep the suits outside where they're dusty and you don't have to clean them up every day, and then once a month we clean them up and bring them in. The other point I'll make that's relevant to future discussion is in the ceiling we have 500 pounds of water, and we use that as radiation protection, but it's also a fusible heat sink. And so we actually built 4 generations of that and did thermal vacuum chamber tests, and it works great. This is a shot from RATS 12 where we actually, this is the third generation of the vehicle. We actually did a 2-week sim on Itakawa. Very detailed stuff. That's what it looks like from the inside. Notice the great windows. I know as geologists you love this, but people are always trying to get me to go with cameras and virtual reality. I said, no, I need the windows. So we have great windows. So this is the PEV with the hopper. We did a pretty detailed conceptual design and MEL, master equipment list, mass estimate of the hopper. And this chart basically shows the mass of the hopper is about 1,461 kilograms. These are 22 regions, which would be 2 full missions to Phobos. And we wanted to see where the break-even point of going with a hopper versus RCS was. And the hopper mass breaks even at 5 to 7 regions if we do only hopping. But we started looking at that, and we tried to do some estimates of the inefficiencies of the soil mechanics. And we basically did a sensitivity study from 10% to 90% mechanical efficiency. And you end up being really slow and probably doing a lot of hops, and then you're wasting power and so forth. And so if we actually go region to region with RCS and then use the hopper intra-region, it starts paying for itself somewhere in the 9 to 14 region area. But the other nice thing about the hopper is that once the crew leaves, if that vehicle is there, the ground can continue to use it. And we did the energetics, and it's amazing. But we could do 135 kilometers of traverses hopping with only 10 kilowatt hours of energy, which is like running your refrigerator for 2 weeks. So it's very effective to hop on Phobos. So the cabin of this PEV is part of this modular exploration system that we've been conceiving, where there's a core cabin that can be outfitted with different end caps and be used as a pressurized excursion vehicle, as a Mars surface vehicle, as a habitable airlock for cislunar space, and as a MAV. In fact, just a few weeks ago, we finished this test where we actually evaluated that cabin as a Mars ascent vehicle, and it actually worked extremely well in that capacity. And in fact, the crew comments were it can't be any smaller, but we don't need it to be any bigger. So I think we kind of nailed the size on that. So we pulled all of this together into this model where we used Copernicus for the estimates of the delta V and the prop going region to region, the Nexus sim for the intra-region hopping and RCS stuff. Logistics, we have a standard logistics model that we use from Langley. And then we pulled all of this together to evaluate different architectures. It generates some 70 figures of merit between all the masses and logistics and EVA, operational efficiency, and so forth. Okay, this slide is about a year's worth of work on one slide. So these are the options that we looked at. One was just nothing pre-deployed. We'd have a PEV taxi that would taxi over from high Mars orbit. We would leave the service module in a 20-kilometer DRO and then fly down to the surface in the PEV. This would be 2 crew for 50 days. I'm sorry about this thing not working so well. These are the masses deployed. We could achieve 100% of our science on those 11 sites in those 50 days. We'd be working hard, but we could do it. Option 2 was 2 PEVs, 1 pre-deployed to Phobos, 1 as a taxi. The next option was a DRO hab and 2 PEVs. And then we looked at a surface hab and 2 PEVs. And then we looked at an absolutely minimal option, which was the MAV basically as a lander, where we would land on Phobos, get out, plant a flag, grab a sample, and come back. And we wanted to sort of bookend this. And then the last one that we spent a lot of time on is a mobile hab. And the idea there is that there's this hab that's mobile that can fly with RCS to all the different sites. Without going into great detail, we're able to cut off our prop and land from about 100 meters up, and the legs stroke, so we wouldn't be pluming the areas of interest. And that would be combined with this minimal taxi that actually would dock to the mobile hab. So these are the estimates of the masses for all these different options. Obviously the ones with just the PEV are a lot lighter. The mobile hab came in much lighter than the full hab with the 2 PEVs and so forth. And then this just shows the percent of the science achieved as a function of days on Phobos for the different options. Most of them did well. You know, obviously the lander case where you jump out and take one sample didn't get a whole lot of the science done. So that's kind of the mobile hab option. And so if we had a mobile hab, we're going to have to be at 14.7 psi because that's what it's basically microgravity on Phobos, and all of our space station countermeasures are developed for 14.7 psi. So in order to do an EVA from a mobile hab, we'd have to do the in-suit light exercise pre-breathe protocol, which takes 3 hours and 39 minutes to get out the door. And then we don our jet packs that we would have as a contingency. Then we assumed very conservatively a 20-minute suit clean and verification. We end up with 4 hours and 44 minutes of overhead, which generates an EVA work efficiency index of 1.37, and that's basically the EVA time divided by the overhead time. If we went with suit ports, and I won't bore you with all these details, we get out the door much faster because we basically have no pre-breathe. We don't have to clean the suits very much. We cut that down to 5 minutes, and we end up with only an hour and 5 minutes overhead, and that's a work efficiency index of 6.0. So even if we had a mobile hab, we would taxi over in this cabin that's a habitable airlock, and then we would camp out in that cabin for 2 weeks at 8.2 psi, 34% oxygen to do our EVAs. So here's the concept design. The legs would be based on the athlete. I think most of you are aware of that from JPL. And the idea is we would use RCS to go from site to site, and then within each site we would ambulate on these athlete legs. And we would have these booms that would deploy off the habitat, and then we could slide along those with our hands, also with foot restraints and body restraint tethers. We'd also be on a tether with a jetpack, and if there would no doubt be some rock you wanted to see that was beyond your reach, and so the idea is you could excurse on tethers so you wouldn't achieve escape velocity and work in that fashion. And we actually built a full-scale functional mock-up of the Phobos hab boom, which we tested a couple years ago on Nemo. If you could run the video, please. Back in the control room. So this is just some quick footage. And it was basically a 25-foot long, had a hypotenuse that we'd lock into place, so it's not a cantilever boom, and it actually had feet that would go down and interact with the surface to transfer some of the crew loads to the surface. Here we are installing the hypotenuse. And you can see there's a tool stanchion and a foot restraint that slide along the boom, and so it's a really nice work platform. And then we could yaw it. We actually were kind of low on funds, so it wasn't electrically actuated. We just used ropes to yaw it, but that worked fine. And it turned out to be a very good, stable work platform. And we actually worked with our EC friends and Paul and others to develop a whole suite of tools for sampling on Phobos that actually worked very well. And it was the big emphasis on not cross-contaminating. And so we basically would get samples and put them away, and then the whole end effector would come off the tool so we wouldn't use it again for another sample. And then we did have grab bags such that once we ran out of these end effectors, we could grab things, and with the baseline and so forth, you could probably deal with the cross-contamination. Okay, well, I'm going to go fast here. Anyhow, without getting into great detail, we measured a bunch of metrics. We have a 10-point Likert scale, and all the crew members felt like it was absolutely fine with no improvements necessary. So it's a good way to go. So in terms of architecture down select, so I talked about 7 different options. We quickly ruled out the orbital habitats with PEV excursions because it was very time and prop expensive to come in from L4 or L5, and even at L1, which is only a couple kilometers away, it was not that great. We also ruled out the short excursion Phobos stays with the PEV just because we didn't get the radiation protection that we wanted. And the mobile hab with the minimal taxi had a lot of advantages. We actually were pretty excited about that for a while, but when we really started thinking about it and running the prop numbers, the 10 region-to-region relocations required about 4,250 kilograms of propellant. And then just the risk of landing that hab, 11 times versus 1 kind of scared us. And then more than anything, the trafficability, moving around with this large hab, we wouldn't be able to get into walls of craters and a lot of the scientifically interesting areas. With the PEV, as we translate region to region, we've got all these instruments that can be collecting data and so forth, and it's much more agile and able to go into scientifically more interesting areas. So for that reason, we down-selected to a predominantly stationary Phobos hab, which would be common with the Mars Transit hab and the Mars Surface hab, a pressurized excursion vehicle that uses the same cabin as the MAV and the Mars Surface rover, a Phobos taxi that uses that MAV cabin and the MAV second stage that transfers the crew from high Mars orbit over to Phobos. And the only unique Phobos elements would be the RCS sled and hopper platform and the Phobos hab landing legs. So I should have said this, but I was militant in this study to not develop things that were expensive and Phobos unique. So almost everything we developed is Mars surface forward. So this is basically our ops concept. The habitat and PEV are pre-deployed to Phobos. The PEV would actually insert into a 20-kilometer Phobos DRO orbit, and the hab would land at landing site 1. And then the crew arrives in the Mars Transit vehicle, and they taxi over in the MAV taxi and meet up with the PEV in the 20-kilometer DRO orbit. From there, you deorbit and rendezvous and dock with the hab that's pre-deployed. We then check out the hab hardware and systems, and we spend a couple weeks doing demonstration PEV functionality, verifying our GNC algorithms and all that kind of stuff. And then after that's all done, and I'll talk about that in more detail, we begin region-to-region exploration. We were concerned with a failed PEV and then how we would rescue that. So I'm going to talk more about that, but at first we said we would stay within 3 kilometers of the habitat. And then halfway through the mission, we would relocate the habitat and then proceed to finish up. When we're done, the crew would transfer into the PEV. That would launch into the 20-kilometer DRO orbit, and then you would transfer back to the Mars Transit vehicle in high Mars orbit, and then go home. So the MAV folks wanted us to look at having the MAV stay with the hab so we could routinely inspect it and so forth. So we looked at that, and I'm not going to bore you with all this, but basically this option is that you would pre-deploy the habitat and the PEV, and then you would transfer directly from high Mars orbit down to the habitat in the MAV, and it would stay docked to the habitat for the whole mission. Everything else is pretty much the same. And then when you go back, you have the advantage that if there's some contingency in the hab, you just get into the MAV taxi and go. You don't have to do this additional rendezvous with the PEV. So there were some things that were attractive about that option. I'm not going to read all of this, but option 1 is that the hab lands solo. The PEV is in the 20-kilometer DRO orbit, and we made up with it. So it's less complicated landing dynamics. It's easier to relocate the hab. And so forth. With the MAV actually attached to the hab, we got into these scenarios that if I had a failed PEV, so I've got 2 people in the PEV, 2 people in the hab, now I need to go rescue it. Do I want to launch my whole hab that has this MAV hanging off of it, or do I send the MAV off? It got fairly complicated. So we basically said, let's start with having the MAV in DRO, and then maybe after we relocate the hab, we could bring it down. The other option was that on some of our longer traverses, we could pop up into DRO and check on the MAV a couple times during the mission. So a lot of this was set by this rescue of the failed PEV. So we wanted to see if we could maybe walk back if the PEV failed. So we did some calculations, and we started out with just jumping, and I weigh about 180 pounds, so I figured, hey, I could at least jump with my own weight. And so we did the calculations. We're good. We did the calculations, and when you jump, you spend a lot of time, a lot of hang time. So you're not really getting very efficient. You spend a lot of time hanging up in the air. So we said, hey, it's probably better to translate prone like we would on space station, and we can go 0.61 meters per second with that. So the jumping technique, which you would never do perfectly, was looking at like 7 to 10 hours for a 10K walk back. The prone technique gets it down to like 5 hours, but there's a huge amount of uncertainty there. We probably think some combination of safer jetpack for attitude control with you pushing off the surface to achieve, the 0.61 meters velocity, but not escape velocity is probably the right answer. We don't really know. We're starting to evaluate these techniques on our gravity offload system at JSC. But anyhow, so going through in a little bit more detail for the timeline. So we have 2 days to activate and check out the HAB. We then do a 1.5 to 4 hour pre-breathe depending on the suit pressure. We egress the HAB airlock. We deploy the outrigger. We do a surface locomotion adaptation. We get a contingency sample. And then we go up into the PEV and transfer into the suit ports. And then we take 2 weeks to verify everything that we thought we knew about Phobos. And this would all be done locally next to the HAP. So we'd evaluate the RCS handling characteristics, targeted burn evaluations, hopper evaluations, all of our EVA methods. We'd verify our prop estimates. And then we'd assess this contingency walk back. So we'd have guys on tether with the PEV following them back and really kind of understand everything that we thought we knew about Phobos. And then we'd actually take 3 weeks then to do LLT of Mars surface assets while the ground replanned our whole flight plan based on the data we got from these tests. And then after that, we fall into a pattern where we'd have 2 week excursions of 2 crew in the PEV, and then the other crew would be in the habitat, and then we'd spend 3 weeks at the habitat with all 4 crew, doing habitat maintenance and LLT of Mars surface assets. I'm going to have to pick it up a little bit here. So as far as LLT, we did a big study that Mike Wright's going to talk about more, but as you all know, to date, all the robotic planetary exploration has been under high or very high latency times. And so we wanted to understand what the characteristics of LLT robots should be so that we could design them in looking forward. And I'm not going to bore you to detail in a lot of detail, but the crew has 6 hours in their shift to do LLT for that 3 week period. In order to maximize the crew productivity, we would want to have faster rovers. I mean, picture a crew doing LLT of Curiosity. I mean, that's not good use of their time. If we assume conventional RTG power sources, we'd probably need to have multiple rovers. And as an example, we kind of scaled up Curiosity and said if we drove it at about 5 kilometers between each site and then spent an hour at each site, it would take 30 hours to recharge. And if we wanted to sleep shift the crew so that they were available to operate this rover as soon as it was ready for us, you end up with some weird sleep shifts where you get up at 8 one day and 11 the next, and that didn't work. So if we wanted to have a regular pattern, we'd only be 43% efficient. So this chart here basically shows the mass of the rover compared to the crew efficiency. And the bottom line is rovers of 250 kilograms or less would be available 100% of the time for the crew to operate. So the notion is we would have this high-powered, low-mass scouting rover with a limited number of scientific instruments on it. We actually have a sim that we're doing now to evaluate speeds as a function of the time delay to get a better handle of that. I'm doing fine, Steve. I'll be about 5 more minutes. So we wanted to understand the power and lighting considerations. And the bottom line is we're either going to pre-deploy the HAB with a 150 kilowatt SEP or a 435 kilowatt chem-SEP hybrid. So we assume 10 and 15 kilowatts as the steady state power load of the HAB. and we looked at all the different regions, and the bottom line is we would be fine as a function of the seasons on Phobos with the HAB pretty much in any one of those 11 regions. So we're fine with power. For the PEV, I won't worry with all of these details, but we would have to sequence the regions based on the season of the year to go there. And there actually are some regions that we couldn't spend the full 2 weeks in because we would run out of power. These just show the solar arrays. We'd probably go with what's called a ROSA array that we actually integrated with our mock-up of the PEV. These are deployable arrays. They would be retracted while we do the site-to-site translations, and the minute we land, we deploy them. Another thing that came up, and I'm not going to bore you with a lot of details, but there's a new technology called a nano flow cell that's basically ionized salt water, and it combines in a half-cell reaction, generates power in neutral water, and doesn't have the risk of explosion of a fuel cell. The electrolyte can be quickly recharged. We're carrying water in this PEV anyhow for radiation protection and a fusible heat sink. And so if we put this nanophase salt in there, we could actually use it for energy storage. And it turns out that this nanophase salt liquid has a specific energy of 600 watt-hours per kilogram, which is about 3 times that of a lithium-ion battery. And so with this technology, we could actually go into some of these regions that don't have enough sunlight and stay there the full 2 weeks without solar rays. Other thing we looked at was HAB docking dynamics. This slide just shows the tilt angle at different docking velocities and then the settling time. And we actually did this in the sim, and it's an eye-opener. Once your velocity vector gets slow, you really see the gravity on Phobos. And so you're doing all these up pulses, and you get cross-coupling. It's very difficult to dock. If you had a failed docking, the HAB is going to tilt, and then it's going to come back at you, and it creates a bad situation. And so the bottom line is, and I won't read all this, we decided that it would be much better to berth than to dock. And so we'd approach the HAB with the astronaut positioning on the front. We'd actually grapple a fixture and then very slowly berth the PEV to the HAB. Last thing is the Eva Force Analysis. A lot of people thought we needed to anchor to Phobos. I have no good ideas how to do that. And it turns out that we use these outriggers that were like the boom I showed you. And without reading all these graphs, basically with a 25-foot outrigger, if an astronaut applied a 20-pound force, you would tilt up 10 degrees you would remain in contact with the surface for about 7 seconds before your arm length of 2 feet would be exceeded. You would actually come up 10 feet off the surface, and it would take you about 60 seconds to come back down. Having said that, a lot of the tasks that we do are very low force, float samples, soil scrapes, and so forth. And as an astronaut, you will quickly understand that if I push straight down, I'm going to go up, so come at it from the side and so forth. And then for the core task and things like that, we would fire our up-firing jets on the PEV to react those forces. And so we feel very comfortable that we could do work without having to anchor. And that's it all. Basically, we can generate up to 8 pounds of force without even tilting the vehicle, and then more than that. And then, of course, we would use the RCS for more. So this is my get off the stage, a couple things here. So we looked at all this architecture. We looked at the capabilities of the ChemSep hybrid to deliver masses to Phobos at different launch dates. And it turns out that this mission closes with 4 to 22 tons of mass margin, depending on the launch date. It also incorporates credible EVA exploration techniques that don't require anchoring, provides 100% of the reference science objectives, 34% reduction in radiation exposure, gives us over 1,800 hours of crew time for LLT of Mars surface assets. And so we think that Phobos is a viable human target, and we're targeting 2031, 2033. Finally, Phobos is an investment in a Mars surface mission. Pretty much everything we have, and these just show all the elements, a lot of them start in cislunar, And pretty much everything that we use on Phobos is Mars surface forward, not just in concept, but literally in the design of the hardware. So the only things that aren't are the RCS sled and the hopper legs of the PEV and then the landing legs of the HAB. So we learned all of this stuff. Additionally, Phobos offers numerous public engagement benefits, including the fact that Phobos is only 9 kilometers from Mars, and Mars will loom large over the horizon of everything we do on Phobos. And you got to believe that if we go to Phobos, the will be there to take the next step to Mars surface. It's also recognized that within the EMC, the Mars architectures we have additional expensive low TRL systems like EDL and nuclear fission and so forth. And so, we could, these Phobos missions will cost money. So, but we could take 15 years and not spend any money and develop all the Mars landing stuff and then go to Mars. But that's probably not a good plan. We want to have a steady pace of development. And so we look at the Phobos mission kind of like Gemini was to Apollo. We're actually buying down risk. We're building the transportation infrastructure and all of that. Play the video, please. And this is a video from our high fidelity physics sim. We're down in the crater with the habitat, and we hop off. That's got to be cool to do that. I mean, and that's a monolith. So that, if you do that, I mean, people are going to be excited about that. And I'm going to end with, we have done a fair amount of work. I don't have time to talk about it, but we have a really cool lander that doesn't weigh that much that could do a lot for us. If one of you guys wants to piggyback that on your science mission, we'd love to talk to you. And that's all I have. Thank you very much.
Okay, quick question, a quick comment. I mean, thank you so much for doing all this. This brings incredible scientific and operational reality to human exploration of Phobos, and it shows why it is in fact, something the feed forward is really critical. All the things you say about preparing, keeping it in the limelight, et cetera, are really, really important. So thanks so much for such a great job. I just had one quick comment on your bookend, plant the flag and collect samples.
Mm-hmm.
I'm thinking, we don't want that flag to fall over. So I'm thinking maybe reverse that, drill a 5-meter core, extract the core, and then put the flag in, because, we don't want to lose the flag, okay?
That would be good. Make sure you get through that Deimos dust, right?
Hey, Mike, thank you as well for all this work. 2 quick questions. One is, have you looked into what's often done in traverses on Earth in expeditions, which is to cache out life support assets, which are then retrievable, so that essentially if you don't need to use these emergency safer supplies, for example, they basically find their way back home, and then you can redeploy them for your.
So, we looked at that, and we certainly will do that on planetary surface stuff.
Right.
But the distances and times on Phobos are not that large, right. And we have significant consumable margin in the PEV for excursions and so forth. Right. So, there is some thought that we could maybe do something if we had some weird Mars surface scenario where we had to abort to Phobos. Right. We'd leave enough consumables there to tide them over until a rescue mission could come, that kind of thing.
Great. And the second question is, what are the next steps in this study, and how do we turn this into reality?
Yeah, that's a great question. We've published a couple papers that I have some copies of. You're welcome to have this. We continue to do the analysis as part of the whole EMC. We're refining the whole MAV taxi and all of that work. That's ongoing. We have missions that look at, if we decide to maybe defer Mars surface longer, where we could do Phobos and Deimos and multiple missions. And with the PEV taxi, we could actually go from Phobos over to Deimos and back and so forth. So we could do a short, maybe a 2-week excursion from Phobos to Deimos. We're also looking at teleoperating assets on Deimos from Phobos, which is actually very exciting. So it's an ongoing thing. we're hoping that the new administration transition team gets in there and gets excited about Phobos and again, because I know we all want to go to Mars surface, I really don't think this is a detraction from that. I mean, everything we're doing is Mars surface forward. And we can talk more later. I think Steve's getting a little antsy here for the timeline.